Greetings. My name is Mike Levis, and I'm an instructor with the Mount Hood Ski Patrol Avalanche Program. Today we continue our deep dive into snow science with Snowpack Part 2. Snow is a very unique material, as we discussed in Part 1. In this module, we're going to do a deep dive into metamorphosis, examining the different kinds of metamorphic processes and the types of snow crystals resulting from these processes. And lastly, we will discuss weather-snowpack interaction. Throughout this discussion, you will be given supplementary material to read. Please make sure you read this material, and don't get behind. The fire hose of snow science material is just starting. We've talked about metamorphism and the effect temperature gradient has on snow crystal formation. Let's get more specific and discuss some examples of this. There are 4 types of metamorphism that we will consider. Initial metamorphism is the change that occurs in newly deposited snow. As the snow accumulates, the temperature gradient determines the crystal type that forms. Changes in the snow layer over time determine stability. Faceted metamorphism occurs in high temperature gradient environments and results in faceted crystals. Examples of faceted crystals include depth hoar, surface hoar, and grauple. Faceted crystals result in decreased snowpack stability. Rounds or rounding metamorphism occur in low temperature gradient environments. Examples of rounds include precipitation particles and rounds. Rounds tend to form well-bonded slabs and increase snowpack stability. Melt-freeze metamorphism occurs when the snow melts and then refreezes. Snow is converted to water, then ice, and cycles between these two states as the temperature cycles. Depending on the state, melt-freeze structures can be either strong or weak. Note that metamorphism is a dynamic, reversible process. The snowpack undergoes continuous change, and changes in temperature gradient can result in rounds being converted to faceted crystals or the reverse. This is particularly true in the top 10 centimeters of the snow surface. Let's take a closer look at initial metamorphism. As snow is deposited, the initial snow crystals are poorly bonded to each other and to the bed surface. Over time, gravity will compact the snow and the crystals will bond to each other and to the bed surface. The strength of these bonds, and hence the stability of this layer, will depend on the type of crystals formed and the size difference between the newly deposited crystals and the crystals on the bed surface. As more snow falls, the effect of gravity and temperature cycling works to continue to compact the snow and increase bonding between snow crystals and form a strong, stable, cohesive layer. Faceting metamorphism results from large temperature gradients in low-density snow. Some examples of faceted crystals are shown in the pictures on this slide. These crystals are highly angular and will bond poorly to adjacent crystals, resulting in a weak layer. Remember our big knobs. Facets form when there's a temperature gradient of 10 degrees C per meter or greater. When the temperature is warm, i.e. near freezing, and the snow is low density to allow room for crystal growth. This slide and the next 2 slides describe the major categories of faceted crystals that we will encounter. Depth hoar are faceted crystals found deeper in the snowpack or near ground level. They could have started out as surface hoar and then been buried by subsequent snow deposition, or they could have been created in the snowpack from localized heating, creating a large temperature gradient. Depth hoar can often be found on Mount Hood in sheltered spots where the snowpack is thin and the temperature gradient is large. Depth hoar can form persistent weak layers that can lie dormant in the snowpack and result in the slide long after they're buried. Surface hoar is frozen dew, characterized by large crystals on the snow surface. It can be found on Mount Hood on cold, clear, calm nights. When surface hoar gets buried, it will form a buried weak layer. Near-surface facets occur due to radiative effects in the top 10 centimeters or so of the snowpack. As with surface hoar, these faceted crystals can get buried under subsequent snowfall and form a buried weak layer. More on these radiative effects later. Graupel, shown in the picture, are balls of ice that act as small ball bearings. Graupel, when buried, forms a weak layer with poor adhesion to subsequent layers. Let's look now at rounds or rounding metamorphism. Going back to our three big knobs, rounding metamorphism occurs when the temperature gradient is small, temperature is warm, that is near freezing, and the snow is higher density, limiting ice lattice voids for crystal growth. Rounding results in small rounded grains that form well-bonded cohesive layers. Rounds form in low temperature gradient environments due to crystal decay or sintering. When you look at rounded snow under the microscope, you typically see round particles bonded to adjacent particles through thin necks, as shown in the top photo on this slide. Sintering is another vapor pressure-driven process that redistributes water molecules between two crystals in contact. Water vapor molecules move from a sharp pointed area on a crystal to a flatter area on the same crystal or an adjacent crystal. Water molecules are redistributed from convex points to concave points, filling in these concave points and forming bonds or necks between molecules, as shown in these pictures. Sintering forms strong bonds between crystals and increases snowpack stability. This slide shows several examples of rounded crystals. The top picture shows sintered crystals, as we discussed in the previous slide. The bottom photo shows precipitation particles, which is basically new snow. The middle photo shows decomposing precipitation particles. Note the rounded arms of the snow crystals. This is characteristic of older snow that has been ground down by wind effects or settlement processes. So let's discuss the fourth metamorphic process, melt-freeze metamorphosis. Melt-freeze metamorphosis occurs when there's a temperature cycling in the snowpack. The snow melts, resulting in increased liquid water, and then refreezes. This results in large clusters of rounded grains when frozen, as shown in the picture. Melt-freeze snow is very weak when melted and strong and stable when frozen. Melt-freeze metamorphosis is quite common on sun-exposed slopes on Mount Hood. Let's dig into this a little more deeply. When snow is at or near freezing, water in the liquid form increases in the snowpack. This can be due to solar heating or rain, for example. Under these conditions, water vapor and liquid water migrate from small grains to larger grains. Water vapor movement is driven by a diffusion gradient, while liquid water migrates due to changes in surface tension. Both processes result in large grains getting larger and small grains getting smaller. Over many cycles, the snow layer results in larger and larger ice crystals and eventually looks like a sheet of ice. The top photo on this slide shows melt-freeze crystals. Note the large, rounded crystals bonded together. Water behavior in snow is very interesting. As you learned in AVI 1, rain adds weight without adding strength to the snowpack. But water is not static. It will migrate through the snowpack through channels running vertically or along horizontal ice layers. When liquid water is migrating through the snowpack, it acts as a lubricant and weakens the snowpack. When it refreezes, it strengthens the snowpack. The bottom photo shows an experiment with red dye to show liquid migration through the snowpack. Red dye was placed on the surface of the snow, and the migration over time into the snowpack was observed. Here is another photo showing liquid water that was migrating through vertical channels in the snowpack, and then refrozen and isolated to clearly show the channels. The channels formed in coarser, more porous grains of snow. Earlier we mentioned that temperature was one of the big knobs determining crystal formation. In many of the earlier slides we discussed that temperature needed to be cold but not too cold. Well, what does this mean? This somewhat confusing graph shows the effect of temperature on the temperature gradient necessary for faceted crystal formation. Vapor pressure is the third variable. As temperature decreases, the rate of crystal formation drops rapidly. For example, if we look at the horizontal axis at minus 5 degrees centigrade, a 10 degrees centigrade per meter temperature gradient is necessary to drive faceting metamorphosis. This is the third curve from the right. At minus 20 degrees C, a temperature gradient of 50 degrees C per meter is necessary for the same rate of crystal formation. So at colder temperatures, the rate of crystal formation slows way down. This means that faceted crystal formation can proceed very slowly and result in deep buried layers that weaken over time. This table is a brief summary of the various metamorphic processes we've discussed. Please take a second to pause the video and review it. We've discussed several common types of crystals in this module: precipitation particles, rounded grains, depth ore, surface ore, and so forth. When we get to our field sessions, we will look at snow grains under magnification and record crystal types in your field notebook. This table is from SWAG and shows some of the common symbols you use to record these crystal types. The table on the right-hand side of this slide is from the SWAG appendix. It shows the International Crystal Classification for snow. I would encourage you to get familiar with the symbols and codes for common crystal types, and we will use them extensively in our data pits. So we've covered a lot of material. As we go forward in subsequent modules, much of what we have covered in these first two parts will be critical in understanding what we see in the Snowpack. We have discussed the four basic metamorphic processes: initial metamorphism, faceting metamorphism, rounding metamorphism, and melt-freeze metamorphism, and discussed the conditions which drive these effects and specific examples of snow crystals resulting from these processes. There's a lot here, and it's the core of our snow science discussion. If you need to watch this video again to grasp all of this, please do so before moving on.